Today I will be presenting the research paper titled Contextual Spelling Correction Using Latent Semantic Analysis. In natural language processing, one of the fundamental problems is not just detecting spelling mistakes, but identifying whether a word is appropriate in this given context or not. Many errors in real world writings are not typographical errors but contextual errors, where the word is valid but used incorrectly. For example, words like affect, effect, quite, quiet are often confused. Traditional spelling checking systems are not capable of detecting such errors because they rely only on a dictionary lookup. If a word exists in the dictionary, it is considered correct, even if it is wrong in context. This paper addresses this limitation by using latent semantic analysis (LSA), which is a method that attempts to understand meaning by analyzing patterns of word usage rather than relying on explicit rules. Now, LSA is a technique used to uncover hidden relationships in text by studying how words co-occur across documents. The central idea is that words are not isolated entities. Instead, they are indicators for underlying concepts. When words frequently appear in similar contexts, they tend to have similar meaning. For example, words like doctor, hospital, and patient often appear together, suggesting that they are semantically related. LSA captures these relationships by converting text into a mathematical form and analyzing patterns within the representation. It does not rely on grammar rules or dictionaries of meanings. Instead, it uses statistical pattern to infer meaning. Originally developed for information retrieval, LSA improved search engines by allowing them to retrieve documents based on meaning rather than exact keyword matches. In this paper, the same idea is applied to contextual spelling correction, which requires distinguishing between words based on their meaning in context. Now, let's see what the problem is. Natural language processing faces several inheritance challenges that makes this task difficult. The first challenge is ambiguity. Many words have multiple meaning depending on the context. For example, the word bank can refer to a financial institution or the side of a river. Without context, it is impossible to determine the intent of the meaning. The second challenge is lack of context understanding in traditional models. Most simple approaches rely on words frequency and treat words independently. They fail to capture relationships between words, which are essential for understanding meaning. The third challenge is the high dimensionality of text data. When text is represented as a matrix, it often contains thousands of dimensions and a large amount of noise. This makes it difficult to extract meaningful information. These challenges highlights the need for a method like LSA that can capture deeper semantic relationships. Now, to understand it better, the motivation behind LSA, consider how humans interpret language. We rarely rely on formal definitions. Instead, we learn meaning through repeated exposure to words in different contexts. For example, even without knowing the exact definition of the word doctor, a person can refer its meaning from a sentence involving hospital, patients, and treatments. Similarly, words like car, automobiles have the same meaning, but they may not appear together in the same sentence. Traditional models fails to recognize this similarity because they rely on exact word matching. Now, LSA is based on the idea that meaning can be inferred from patterns of word usage. By analyzing large collections of text, it identifies relationships between words and uncover hidden semantic structures. Now let's discuss the core idea. The core idea of the LSA is to represent word and documents as vectors in a high dimensional space. Each word is assigned a vector based on how it appears across different documents. Words that occur in similar context will have similar vector representation and will be located closer to each other. In this space, this allows us to measure similarity usage geometric concepts such as distance and or angles also. In this way, LSA transforms the problem of understanding language into a mathematical problem. Instead of relying on rules, it uses patterns and geometry to capture meaning.
So let us now move from the conceptual understanding of text to its mathematical representation, which is the foundation of latent semantic analysis, which we can say as LSA. To apply LSA, we first convert textual data into a structured numerical format known as a term documented matrix. Here, T represents the number of unique terms and D represents the number of documents in our dataset. So each now corresponds to a word and each column corresponds to a document. The value inside the matrix represents how frequently a particular word appears in a given document. This could be raw frequency or something sometimes weighted using techniques like TF-IDF to give more importance to informative words. Now, why do we need this matrix? Before, because computers cannot directly understand text, but they can process numbers. So, this matrix acts as a bridge between language and mathematics, right? However, these are important challenges with this representation. First, the matrix is usually very large, especially when dealing with real-world datasets containing thousands of documents and tens of thousands of unique words. Second, it is extremely sparse, meaning most of the entries are zero. This happens because each document contains only a small subset of all words. Third, the many words such as the, is, and appear very frequently but do not carry meaningful semantic information. These words can dominate the matrix and distort analysis. Additionally, this representation does not capture deeper relationships between words. For example, two words with similar meanings may never appear together, yet appear so basically, as they are conceptually related, the raw matrix fails to capture such hidden connections. Because of these limitations, simply using the 10 document matrix is not sufficient. We need a way to extract the underlying structure, reduce noise, and identify meaningful patterns. This leads us to the core mathematical tool used in LSA, which is singular value decomposition. Now, let us discuss the most important mathematical concept behind LSA, which is singular value decomposition, commonly known as SVD. SVD is a powerful matrix factorization technique that allows us to break down a complex matrix into a simpler and more interpretable components. Mathematically, we decompose the term document matrix X as X equals to T multiplies S multiplied the power of T. So here each component has a specific meaning. The matrix T represents the relationship between terms and latent concepts. Each column in T corresponds to a hidden semantic dimension. These are not directly observable but are learned from patterns in the data. The matrix S is a diagonal matrix containing singular values. These values are extremely important because they indicate the strength or importance of each latent dimension. Larger values correspond to more significant patterns in the data. The matrix D transpose represents documents, projects into this semantic space. It tells us how each document relates to a latent concepts. So here the matrix. So here, if you observe the figure on the slide, you can see how the original matrix is decomposed into the three similar matrices. This decomposition helps us separate meaningful structure from random noise. One important intuition here is that SVD helps us uncover hidden relationships. For example, even if two words never appear together, SVD can identify that they occur in similar context and therefore are semantically related. Or in other hands, instead of directly analyzing raw word counts, we are now analyzing patterns of co-occurrence, which give us a deeper understanding of language. This transformation is what makes LSA powerful. It moves from surface level representation to latent semantic structure. Now, after performing SVD, we obtain multiple dimensions or components. However, not all of these dimensions are equally useful. Many of them correspond to noise, redundancy, or less significant patterns in the data. To address this, we perform dimensionally reduction, where we retain only the top k most important dimensions. Mathematically, we approximate the original matrix as xk equals to tk multiplies sk minus d transpose k. So here we give only the top k singular values and their corresponding vectors. Now, what does this mean initiatively? We are essentially compressing the data while preserving its most important structure. It is similar to summarizing a long paragraph into key points without losing the main idea. If you look at the figure on the slide, you can observe that the matrices become smaller after reduction. This not only reduces computationally complexity, but also removes noise. This reduced representation is called a low rank approximation of the original matrix. One key advantage of this step is that it helps in generalization instead of memorizing exact word occurrences. The model focuses on border patterns and relationships. For example, even two words never appear together. They may still be close in the reduced space because they share similar contexts. Choosing the value of k is important. If k is too small, we may lose important information. If k is too large, we may retain noise. So, selecting an optional value of k is crucial for performance. Overall, dimensionality reduction is a step that transforms raw data into a meaningful and compact representation. Finally, after dimensionality reduction, we obtain what is called a semantic space. Right? In this space, both words and documents are represented as vectors in a lower dimensional coordinate system. Now, instead of comparing words based on exact matches, we compare them based on their positions in the space. Words that are close to each other in this space are considered semantically similar. For example, words like doctor, nurse, and hospital may cluster together because they frequently appear in similar contexts. This is a very powerful idea because it allows us to capture meaning, not just surface level text. We can also measure similarity between words using mathematical techniques such as cosine similarity. This helps in applications like information retrieval, document clustering, and recommendation systems. Another important advantage is that LSA can capture synonymy different words with similar meanings and partially handle polysemy, where a word has multiple meaning depending on context. For instance, the word bank could mean a financial institution or a riverbank. Depending on this context, the position is the semantic space may shift accordingly. So, this geometric interpretation of language is what makes LSA so elegant. It transforms language into a mathematical space where relationships can be measured, visualized, and analyzed. In summary, the semantic space allows us to move beyond simple word counting and instead understand the deeper structure and meaning of text.
During the training phase, the model begins by constructing a term document matrix using a large collection of text. In this paper, the brown corpus is used as the data set, and an important design choice made by the authors is that each sentence is treated as an individual document rather than using full documents. This is particularly useful for the task of contextual word prediction as it allows the model to focus more precisely on the local context of the surrounding word. Before constructing the matrix, several pre-processing steps are applied to improve the quality of the presentation. These steps ensure that the data is consistent, meaningful, and suitable for mathematical analysis. For example, the context around the target word is reduced so that only nearby words are considered. This helps eliminate noise from distant words that may not contribute significantly to the meaning of the sentence. Once pre-processing is completed, the term document matrix is constructed where each row corresponds to a word and each column corresponds to a sentence. The values in this matrix are not just simple counts, they are weighted to reflect the importance of words based on their usage. After constructing this matrix, singular value decomposition is applied to factorize it into three components. The matrix is then reduced by keeping only the most important dimensions, resulting in a low dimensional semantic space. This semantic space captures the relationship between the words and their context, allowing the model to understand which words are likely to appear together and how they are related in meaning. Pre-processing is a crucial step in the LSA pipeline as it directly affects the quality of the final semantic representation. Without proper pre-processing, the model may capture noise rather than meaningful patterns. One important step is context reduction. Instead of considering the entire sentence or document, only a limited number of words surrounding the target word are used. This ensures that the model focuses on the most relevant context for predicting the correct word. Another key step is stemming, where words are reduced to their root forms. For example, words like running, runs, and ran are all converted to run. This helps in treating different variations of the same word as a single entity, reducing redundancy in the data. The model also makes use of bigrams, which are pairs of adjacent words. Bigrams help capture local relationships between words that may not be evident when considering individual words alone. For example, phrases like New York or high school carry more meaning together than separately. Finally, term weighting is applied to assign importance to words. Words that appear frequently but carry little meaning, such as common stop words, are given lower weight, while more informative words are given higher importance. This helps the model focus more on meaningful features during analysis. Once the model has been trained and semantic space has been constructed, it can be used to predict the correct word in a given sentence. The prediction process begins by taking a sentence that contains a target position where a word needs to be selected. For each confusion set, multiple candidate words are possible. The model inserts each candidate word into the sentence one at a time, creating multiple versions of the same sentence. Each modified sentence is then converted into a vector representation in the semantic space. This representation reflects how well the sentence aligns with the patterns learned during training. To determine which candidate word fits best in the context, the model computes the similarity between the sentence vector and the vector representation of each candidate word. This similarity is calculated using cosine similarity, which is defined as the dot product of two vectors divided by the product of their magnitudes. In simple words, cosine similarity measures how closely two vectors point in the same direction. A higher similarity indicates that the word fits better within the context of the sentence. The model then selects the word with the highest similarity score as the correction prediction. This approach allows the model to choose words based on their contextual meaning rather than just frequency. The experimental setup for this study is designed to evaluate the effectiveness of LSA in contextual word prediction. The brown corpus is used as the data set and it is divided into training and testing sets in an 80 to 20 ratio. This ensures that the model is evaluated on unseen data, providing a fair measure of its performance. The experiments are conducted using 18 confusion sets, each consisting of words that are commonly misused in real-world writing. These confusion sets include examples like effect, effect, quiet, unquiet, there, and many more. This table shown on this slide represents the baseline performance for these confusion sets. The baseline model is a simple approach that always selects the most frequent word from the training data. For each confusion set, the table shows the number of training and testing examples, the most frequent word, and the accuracy achieved by the baseline model. While the baseline may achieve reasonable accuracy in some cases, it does not consider the context in which words are used. This means that it cannot truly solve the problem of contextual spelling correction. This table is important because it establishes a reference point. It shows how well a simple method performs and highlights the need for a more advanced approach like LSA, which can take contextual information into account.
So now let us examine the results of the study in detail, which are presented using both a table and a graphical comparison. The table shown on the slide presents the performance of latent semantic analysis in a comparison with a baseline method and another approach known as tribase. Each row in the table corresponds to confusion set which consist of words that are used commonly misused such as affect, effect or quite and quite. So for confusion set, the table provides the accuracy of the baseline method, the accuracy using LSA and the accuracy using Tribase. The baseline method simply predicts the most frequent word from the training data and does not take context into account. As a result, which may not perform reasonable well in some cases, it does not truly solve the problems of contextual word prediction. Where we compare the baseline results with those of LSA, we observe a clear improvement across most confusion states. For instance, in cases like principal and principal, the baseline accuracy is relatively low, whereas LSA significantly improves the prediction accuracy by utilizing contextual information. This demonstrates that LSA is capable of capturing semantic relationship between word and using them effectively for predictions. Another important observation from the table is that LSA performs particularly well when the confusion sets consist of well word belonging to the same part of speech. This is because LSA focuses on semantic similarity rather than grammatically structure. In contrast, where grammatical differences become important, the performance may not be strong. As we compare LSA with Tribase, we say that Tribase sometimes achieves higher accuracy in certain confusion sets. This is because Tribase incorporate probabilistically and syntactical information, which gives it an advantageous in case where a grammatical structure plays a significant role. However, despite this, LSA still performs competitively and consistently more over baseline method. So the graph shown alongside the table provides a usual representation of these results. In this graph, horizontal axis represent the different confusion sets, while the vertical axis shows the improvement in accuracy over the baseline. Each confusion set is represented by two bars. One is for LSA and another is for Tribase. From the graph, we can clearly observe that LSA consistently achieves positive improvement over the baseline in most cases. The height of each bar indicates that magnitude of improvement, and in it several cases the improvement is quite substantial. So at the same time, we can also see the Tribase outperforms LSA in certain confusion sets, particularly those involving grammatical distinctions. So overall, both the tables and the graph together demonstrate that LSA is an effective method for contextually word prediction, and it significantly improves performance over the baseline by capturing semantic relationships. Even though it may not always perform, that models explicitly incorporate semantic information. So, whereas limitations, despite the strong performance demonstrated by latent semantic analysis, the paper also highlighted several important limitations of the method. One of the primary limitations is that LSA does not explicitly consider grammatically structure of or one word order. It reads text as a collection of words rather than a sequence, which means that is may failure to capture synthetic relationships that are important for understanding meaning. As a result, in such cases where grammatically structure plays a key role, the predictions made by LSA may not always be accurate. Another limitation is that LSA can be influenced by patterns in the training data since it relies on statistical relationships. Frequently occurring words or patterns may dominate the representation. This can lead to biased predictions, especially in the confusion sets where one word appears much more than often the another example. So, for example, in cases like amount and number, the model may favor the most frequent word even when it is not the correct choice in a specific context. Additionally, the performance of LSA depends upon the choice of parameters, particularly the number of dimensions retained after dimensionality reduction. It is few dimensions are retained. Important important semantic information may be lost. On the other hand, if too many dimensions are retained, noise may remains in the data. Therefore, selecting an appropriate value for this parameter is crucial for achieving optimal performance. This limitation suggests that while LSA is powerful for capturing semantic relationships, it may need to be combined over methods that incorporate synthetic or grammatical information to achieve better overall performance. So, in conclusion, latent semantic analysis provides a powerful and elegant approaches to understanding languages using mathematical techniques. By representing text in a vector space and applying dimensionality reduction, It is able to uncover hidden semantic relationships that are not immediately apparent in raw text. The results presented in the paper clearly shows that LSA is effective for contextual word prediction. It consistently improves accuracy over baseline methods by utilizing contextual information and capturing patterns of word uses. So, one of the significant contributions of his work is that demonstrating that word meaning can be extracted from statistical patterns in languages without relying on explicitly grammatical rules or predefined dictionaries. This highlights that potential of data driving approaches in natural language processing. At the same time, study also acknowledges that the limitations of LSA, particularly its inability to capture grammatical structures and its sensitive to parameter choices. So overall, this paper shows that analyzing patterns of word uses is a powerful way to understand language, and it establishes latent semantic analysis as an important method in the field of natural language processing.
Let's try to understand the problem this paper is trying to solve. In earlier NLP systems, words were treated simply as numbers or IDs, which means the model had no real understanding of their meaning. For example, words like king and queen are clearly related to us, but to the model they appear completely unrelated. Another major limitation comes from older approaches like n-gram models. These models only consider a very small context, just a few nearby words, so they fail to capture long-range relationships in language. On top of that, when the dataset becomes large, training such models becomes very slow and computationally expensive. So overall, there are two key problems. First, the lack of understanding of relationships between words, and second, poor efficiency when working with large datasets. Because of these limitations, we need a better way to represent words, one that allows the model to capture meaningful relationships while also scaling efficiently to large amounts of data. So now that we have understood the problem, let's see what solution this paper proposes. The key idea is simple but powerful. Instead of representing words as just IDs, each word is represented as a vector. These vectors are learned so that similar words are placed close to each other in the vector space. So words like king and queen are now related, not completely separate. To achieve this, the authors propose two models, CBOW and skipgram. We'll understand them in detail shortly, but for now, just note that they are simple, powerful, and can learn from very large datasets. One major advantage is efficiency. These models are fast, accurate, and can be trained on billions of words much more easily than older models. Also, these vectors capture not just meaning but grammar too. For example, king and queen show a semantic relationship while run and running show a grammatical one. So overall, the goal is to learn word representations that capture relationships between words while remaining fast and scalable. Now let us see how these word embeddings actually capture relationships. Word embeddings are not just used to find similar words, they can capture different types of relationships between words too. A single word can be similar to others in multiple ways based on meaning, grammar, or even word structure. For example, words like running, walking, and swimming share similar endings, so they tend to group together in the vector space. Now comes the most powerful observation. We can perform simple mathematical operations on these word vectors and they produce meaningful results. King minus man plus woman gives to queen. This means that if we take the concept of king, remove man and add woman, we get something very close to queen. In other words, the model has actually learned the concept of gender difference. And what makes this truly impressive is that we never explicitly told the model what gender is. It learned this automatically just from the data. So instead of simply storing the words, the model is learning how words are related to each other in a meaningful way. The goal, therefore, is to learn word vectors such that these relationships are preserved as accurately as possible. Of course, the quality of these relationships depends on factors like the amount of training data and the size of embedding vectors. Before CBOW and skipgram model, Word representations were learned using Neural Network Language Models (NNLM). These use a standard neural network with input, hidden, and output layers to predict words and learn embeddings. So they were already learning word representations, but there was a major issue. These models are computationally very expensive because they try to solve a few full language modeling problem. Instead of learning relationships, they predict entire word sequences, which makes the task much more complex. The total training cost can be written as O equal to E cross product T cross product Q. Here E is the number of epochs, T is the number of words, and Q is the computation per training step. The key point is that Q is the most critical factor. If we reduce it, training becomes much more faster. And thus exactly what this paper does. It proposes simpler models that reduce computation while still learning good word representations. Now let's understand how NNLM actually works, and more importantly, why is it inefficient. NNLM is a feed-forward neural network that predicts a word using a fixed number of previous words. For example, in the sentence "the cat is," the model uses the cat and is to predict the next word. The architecture is simple. An input layer takes the context words, a projection layer converts them into vectors, and a hidden layer processes the information, and an output layer predicts the next word. The main issue comes from the computational cost, which can be written as Q equal to N cross D plus N cross D cross H plus H cross V. Here n is the number of context words, d is the vector dimension, and h is the hidden layer size, and v is the vocabulary size. The biggest problem is the h cross v term, because the model has to compute probabilities for every word in the vocabulary. Since the vocabulary can be extremely large, tens or even hundreds of thousands of words, this makes the model very slow. So the main bottleneck in NNLM is this large vocabulary computation, which significantly increases the cost. And this is exactly what Word2Vec tries to fix by reducing this computational complexity. So after seeing the limitations of NNLM, researchers tried to make these models faster. One key optimization is hierarchical softmax, where words are arranged in a binary tree. Instead of checking all words, the model follows a path in the tree, reducing computation from V to log V. Another improvement is the recurrent neural network language model, RNNLM. It uses a hidden state to remember past information, allowing it to capture longer context and better language patterns. However, even with these improvements, the computational cost is still high, which is Q equal to H cross H plus H cross V. The main issue is again the H cross V term, which depends on the large vocabulary size, making the model very slow. So, although these models improve performance, the core problem of heavy computation is not fully solved. This is where Word2Vec comes in.
Optimize it for speed. So now we finally come to the main contribution of this paper. How what to make makes everything fast and efficient. The first key idea is model simplification. Earlier models like NNLM and had complex architectures with hidden layers, which made them slow. But what to make simplifies this. It actually removes the hidden layers and uses a simpler structure. Because of this, the computation becomes much faster. Also, these models can be trained using parallel and distributed system, which makes and larger datasets easily trainable. So overall, simpler model plus parallel training gives us high speed. Now let's look at the first model SIBO, which stands for continuous bag of words. The idea is very simple. We use the context words to predict the current word. For example, I love dash very much. Here, I love very much are the context words, and we have to predict the missing word here. So now SIBO tries to find the target word with the help of context. And whereas skipgram model, it is just the opposite way how the SIBO works. Here we use the current word to predict the context word. For example, if the input word is coding, the model predicts surrounding words like I love very much. It may be some random words also. One line summary to say about scriptgram is it finds the target word which is a context word. So key comparison between the difference is prediction. which SIBO predict from context and skipgram predict the context. So earlier we briefly saw what SIBO does. Now let's understand how it actually works internally and how it get the context words as the output. In SIBO, we take the context words, convert them into vectors and then combine them. This combined representation is then used to predict the target word. So essentially, we are using surrounding words to guess the missing word. Now let's understand step by step of the working model. For example, following the three steps shows on the slide. Take context words. First, we take the context word as input. For example, I love very much. So the input will be I love very much. Now combine context words and then we average them. This is very important. Instead of complex neural layers, we just take the average. This is what Stebo makes very fast. And finally, using the average vector, the model predicts the missing word. It may be coding. And this diagram shows the same flow. Context words come in, get combined, and then predict the output. And when we talk about the computational complexity, this is very much efficient compared to NNLMs because here we are not using more complex convolution layers, and we also removing the hidden layers and reducing the heavy computations. And it uses simplest averaging instead of complex neural computations. This is which makes it very much faster compared to NLLMs. Now let's look at the second model, scriptgram. Earlier in SIBO, we used context words to predict the target word, but skipgram does the exact opposite thing. In skipgram, we take the current word as input and try to predict the surrounding context words. So instead of context to word, we now have word to context. So uh, firstly, we will take the current word and let's take the word as example as coding. Now we convert it to vectors. Then we convert this word into vectors representation. This vector captures the meaning of the word. Now using this vector, the model predicts surrounding words like I, love, very much, in or any other words which are related to the vector we found earlier. And one more important thing is skipgram gives more importance to nearby words and less importance to distant words. So closer words are sampled more frequently. When we talk about computational complexity, uh, we have a formula here which we are showing on the slide. So let's compare it with the SIBO model. Skipgram has slightly higher cost because it predicts multi-context words, where comparing to SIBO. But there are some advantages. Skipgram works very well for rare words because it learns more detailed relationships between words. So to quick compare between models, SIBO faster, works well for frequent words, and whereas scriptgram slightly slower but better for rare words. As we discussed earlier, this slide shows the architecture of SIBO and scriptgram. On left side of the SIBO, it takes multiple context words as input. Their vectors are combined usually by summing or averaging, and then the model predict the target word. So to tell about SIBO in one line, context word, it gives a combining and we predict the word. And on the right is skipgram. Here we take single word as input, convert it into a vector, and then predict multiple context words around it. So skipgram is word gives us the prediction of surrounding words.
So, to evaluate the quality of word embeddings, the authors use analogy based text instead of simply similarity. There are two types of relationship tested: semantic and syntactic. Semantic like country and capitals, syntactics like grammar forms. For example, Athens is to Greek and Oslo is to Norway, and big is to the biggest, and small is to the smallest. The model solves this using vector arithmetic, and the answer is correctly only if it is exactly matches the expected word. The key idea is that model learns relationship between words in vector space. So, for example, biggest minus big plus small gives smallest. This words shows that relationship between these are stored as consistent vector differences. And importantly, this model learns both meaning and grammar without being explicitly programmed. So overall, word to vector learns relationship, not just individual words. So in this slide, the table shows the different type of relationship used for evaluation. There are two main categories: semantic relationships like country, capital, comma, currency, or genders. Syntactic relationship like grammar changes such as tenses, plural, and adjectives. For example, Athens Greek and Oslo, Norway represents capital relationships, and brother sister shows gender relationship. On the syntactic side, words like think, thinking, or mouse, mic shows grammar transformations. So the model is tested on many such pairs to check whether it is correctly captures these relationships. So if the model can solve this correctly, it means it has learned both meaning and grammar effectively. So now let us see how data size and vector size affect the performance of word to vector. So there are two main factors: the amount of training data and the dimensions of the word vectors. From the experiments, we observed that increasing of training data improves accuracy, and increasing of vectors dimensions also improves performance. This is because more data helps the model learns better relationships, and larger vectors can capture more information. So the models are trained on a very large data sets, about 6 billion words, which shows the large scale data is important. So this table shows that both data size and vector dimension increases, the performance consistently improves. So overall better performance comes from more data and higher dimension embedding. Let's compare the performance of different models. The models were evaluated on the both semantic and syntactic tasks. From the results, we observed that skipgram performs best on semantic relationships, meaning it captures word meaning very well. SIBO performs well on syntactic tasks, and it also faster to train. On the other hand, older models like NNLM and RNNLM are very less efficient and performs worse overall. This shows that word-to-vector models CBOW and SkipGram are both more efficient and more accurate than previous approaches. So the table here supports these results, showing higher accuracy for SIBO and SkipGram. So overall, word-to-vector provides a better balance of speed and performance. So let's look at the final results of the paper. From the experiments, we observed that SIBO performs well on syntactic relationships and it is faster to train. SkipGram performs best on semantic relationships and achieves the highest overall accuracy. For example, SkipGram reaches around 50% of accuracy, whereas syntactic toss receives 55% of, making its best performance model. This confirms that both models are efficient and highly effective. SIBO versus skipgram. Now comparing SIBO versus skipgram in terms of speed and accuracy. SIBO is faster, it can be trained in all about 1 day, while skipgram takes longer, around 3 days. However, skipgram gives better accuracy, especially for semantic relationship, where SIBO on the other hand performs well on syntactic tasks. So there is a clear trade-off between speed and accuracy. SIBO is faster while skipgram is more accurate. So overall, word-to-vector provides an efficient way to learn meaningful word representations and balancing speed and accuracy, and has become a foundation for modern NLP models. So now let us understand the effect of data size versus training epochs. Experiment shows that increasing the amount of training data improves performance more than increasing the number of epochs. In fact, training on more data for just one epoch can give better or similar results compared to training multiple times on smaller data. This highlights that having more data is more important than repeating training. So large scale training results. The models were trained on very large data sets up to 6 billion words using distributed systems. From the results, we can see that CBO gives best performance while with fast training. Skipgrams achieves the best overall accuracy. And older models like NNLM and are slowly and less efficient. So overall, we can say that this result shows that one-to vector models are scalable and work very well on large data sets.
Now, let's look at how these models perform in real-world tasks. The models were evaluated on a task called the Microsoft Sentence Completion Challenge. From the results, we observe that skipgram performs well on its own, but when combined with RNNLM, it achieves the best accuracy. So, this shows that our word embeddings are not only useful on theoretical tasks, but also works effectively in real-world NLP applications. So, it also shows that these embeddings can be further improved when combined with other models. So overall world to vector is both practical and powerful in real world scenarios. Here, this slide explains the real world task used for evolution. The Microsoft sentence completion challenge. In this task, the model is given a sentence with a missing word and it has to choose the most appropriate word based on context. So, using skipgram embeddings, the model scores different possible sentences and selects the best one. The result shown the skipgram performs well, but combining it with RNNLM gives the best accuracy around 58.9%. But combining it with RNNLM gives the best accuracy, right? So this shows that word embeddings are useful in real world tasks and can be further improved by combining with other models. Now, this slide shows different examples of relationships learned by the model. The model learns meaningful relationships using vector arithmetic. For example, Paris minus France plus Italy gives Rome. This means the model understands relationships like country, capital automatically. Similarly, it learns relationships like to bigger, Japan to Tokyo, and Microsoft to Windows. So the model is not just learning words, it is learning how words are related to each other. And these relationships include both language patterns and real world knowledge. Finally, let's look at the key insights and limitations. The results show that word embeddings are very powerful and can capture both semantic and synthetic relationships. However, the accuracy is not perfect, so there is still room for improvement. What are the improvements are performance can be improved by using larger datasets, increasing vector dimensions, and combining embeddings with other models. Overall, this paper shows that simple and efficient models like SIBO and SkipGram can learn high quality word representations at scale. And this is why word to vector became a foundation for many modern NLP systems. Present a very important concept in natural language processing, which is global vector for word representation. Before we directly jump into global vector, let us first understand the broader picture. In artificial intelligence, especially in NLP, the main challenge is enabling machines to understand human language. So, humans naturally understand words, meanings, relationships, and many, like context and even subtle nonsense. But for machines, everything must be converted into numbers. So, the fundamental question arises what it is. How do we convert words into a mathematical form while preserving their meaning? This is where word embeddings come into play. Word embeddings are numerical vector representations of words that capture semantic meaning. Now, global vector is one of the most influential and powerful word embedding techniques developed to address this challenge. It not only represents word as vectors, but also ensures the relationships and between words are preserved in a meaningful way. In this presentation, we will walk through the motivation problem, which is formulation, mathematical initiation, training, and mechanism, evolution, and finally the advantages and uh, limitations of global vector. Now here we are going to see the problem statement of this in a conceptual depth. Now let us define the problem. In NLP, the central problem is how do we represent the meaning of words in a continuous vector sparse? A good word representation should satisfy multiple conditions. First, it should capture semantic similarity. Words like car and vehicles should be close in vector space. Second, it should preserve relationships. For example, king minus man plus woman should result in a queen, right? So the third one was it should be computationally efficient and scalable to large datasets. However, existing methods fail to achieve all this together. One-hot encoding fails completely in capturing meanings, and word-to-vector captures local relationships but misses global structure. Matrix factorization methods capture global information but are not efficiently. So the key challenge is to design embeddings that preserves both semantic meaning and relational structure simultaneously. So here where the global vector comes. Global vector addresses this challenge by introducing a novel way of using co-occurrence statistics to learn embeddings. Now here we are going to see the problem statement of this in a conceptual depth. Now let us define the problem. In NLP, the central problem is how do we represent the meaning of words in a continuous vector sparse? A good word representation should satisfy multiple conditions. First, it should capture semantic similarity. Words like car and vehicles should be close in vector space. Second, it should preserve relationships. For example, king minus man plus woman should result in a queen, right? So the third one was it should be computationally efficient and scalable to large datasets. However, existing methods fail to achieve all this together. One-hot encoding fails completely in capturing meanings, and word-to-vector captures local relationships but misses global structure. Matrix factorization methods capture global information but are not efficiently. So the key challenge is to design embeddings that preserves both semantic meaning and relational structure simultaneously. So here where the global vector comes. Global vector addresses this challenge by introducing a novel way of using co-occurrence statistics to learn embeddings.
Now let's see what is GLOVE. GLOVE stands for Global Vectors for Word Representation. It is based on very simple but powerful idea. Instead of predicting words directly, we use the statistics of how often words appear together. We construct a co-occurrence matrix where each element xij representing how often word j appears in the context of word I. Now instead of directly using these counts, GLOVE learns vector representation such that the dot product of vectors reflects their co-occurrence relationships. So essentially, GLOVE transforms statistical information into geometrical relationships in vector space. This is a very elegant idea because it connects probability with linear algebra. Now, now, let's see what the co-occurrence matrix is. Co-occurrence matrix is the foundation of GLOVE. It is constructed by scanning the entire corpus and counting how many often words appear near each other within a fixed window. For example, consider the sentence the ice is cold. Here, ice appears near coal, so their occurrence value increases. Similarly, steam is hot. Steam appears near hot, so over a large corpus, these patterns become very strong signals. Now, what is interesting is that words that appear in similar contexts tend to have similar meanings. For example, cold and chilly will have similar co-occurrence patterns. So, by analyzing these patterns, we can capture semantic meaning. This is the key insight behind distributional semantics. You shall know a word by company it keeps. Now let's see the key idea. The most powerful idea in GLOVE is the use of probability ratios. Instead of looking at raw counts, GLOVE compares probabilities. For example, we compare how likely a context word appears near two different target words. This ratio helps us identify relationships. Why is this important? Because raw counts can be noisy and misleading, but ratios highlight meaningful differences. For example, if ice appears much more frequently with cold than hot, this ratio tells us something important about their relationship. Their approach allows Glow to filter noise, focus on meaningful connections, and capture deeper semantic structure. This is what makes Glow more powerful than previous methods.
Moving to the mathematical intuition behind glove, the main goal of glove is to learn word vectors such that their dot product approximates the logarithm of how often two words appear together. To understand this simply, if two words frequently occur together, their vectors should be similar, meaning they point in similar directions. If they rarely appear together, their vectors should be far apart. We use the logarithm of co-occurrence counts because raw counts can vary a lot. Some word pairs appear extremely often while others appear very rarely. Taking logarithm reduces this variation and makes learning more stable. So essentially, glove converts statistical information into a geometric form. Words are represented as vectors in space and relationships between words are captured through distances and directions. This is powerful because language is no longer just text, it becomes something we can analyze mathematically using vector operations. To make this idea work in practice, Glove defines a cost function that the model tries to minimize during training. The purpose of the cost function is to measure how close our predicted values are to the actual co-occurrence values from the data. More specifically, for each pair of words, the model predicts a value using the dot product of their vectors and then compares this prediction to the logarithm of their actual co-occurrence count. The difference between these two values represents the error. Now, if we simply minimize this error directly, the model would face two major problems. Firstly, very frequent word pairs like the and is would dominate the learning process because their counts are extremely large. Secondly, very rare co-occurrences might introduce noise because they may not be statistically reliable. To solve this, Clow introduces a weighing function. This weighing function assigns different importance to different word pairs. For example, very rare co-occurrences are given low weight since they may not be reliable. Extremely frequent co-occurrences are also down-weighted so they don't dominate the model. This creates a balance. The model focuses more on moderately frequent and meaningful relationships which are often the most informative. Additionally, the use of logarithms in the cost function ensures that extremely large values do not overwhelm the optimization process. So overall, the cost function in Glove is carefully designed to ensure stability in training, balanced learning, and better representation of meaningful word relationships. This is one of the key reasons why Glove performs so well in practice. The training process is based on weighted least squares optimization, which simply means the model tries to minimize the weighted error we discussed earlier. This process is iterative and happens in multiple steps. Firstly, the model starts by initializing all word vectors randomly. At this stage, the vectors do not carry any meaningful information. Next, for each pair of words in the dataset, the model computes a prediction. This prediction is obtained by taking the dot product of their vectors along with bias terms. Then this predicted value is compared with the actual value, which is the logarithm of the co-occurrence count. The difference between the predicted and actual value gives us the error. Now comes the learning step. The model updates the word vectors in such a way that this error is reduced. Importantly, each word pair contributes differently to this update, depending on its weight from the weighting function. So more reliable and meaningful co-occurrences have a stronger influence while less reliable ones have smaller impact. This entire process is repeated again and again across the dataset. With each iteration, the vectors gradually adjust themselves, capturing more and more meaningful relationships between words. Eventually, the model reaches a point where the error cannot be reduced significantly further. This is called convergence. At this stage, the word vectors are considered trained. So overall training in Glove is gradual refinement process where random vectors evolve into meaningful representations through repeated optimization. After the training process is complete, what we obtain is a set of dense vector representations for each word in the vocabulary. These vectors are not just random numbers anymore. They encode rich linguistic information. Each word vector captures the meaning of the word, the context in which it appears, and its relationships with other words. One of the most fascinating aspects of these embeddings is that they allow us to perform vector arithmetic to uncover relationships. For example, king minus man plus woman means queen. This means that if we take the vector for king, subtract the vector for man, and then add the vector for woman, the resulting vector is very close to the vector for queen. This shows that the model has successfully captured the concept of gender relationships in its vector space. Similarly, words with similar meanings like car and automobile will be located close to each other in this space. So distances in this vector space correspond to semantic similarity. In other words, glove transforms language into a structured mathematical landscape where meaning is encoded in positions and relationships between vectors. This representation is extremely useful and forms the foundation for many modern NLP applications such as text classification, machine translation, and semantic search. So, to conclude, the output of glove is not just a set of vectors, it is a powerful mathematical representation of language itself.
Glove is evaluated using multiple benchmark tasks to measure its effectiveness. One important evaluation is the word analogy task, where the model must understand relationship between king man plus woman equal to queen. This checks whether the model captures semantic relationships correctly or not. Another evaluation is word similarity, where the model's output is compared with human judgments to see how well it understands similarity between the words to words. So, additionally, named entity recognition is used to test real world applications such as identifying names, places, and organization in text. So, overall, this evaluation together ensures that Glove is not only theoretical but also practically used in real world NLP tasks. So where has the result is Glow performs better than many baseline models like simple co-occurrence or one-hot encoding. So its strengths come from combining both global statistics and local content information, which allows it to capture deeper linguistic patterns. So we also observe that increasing the vector size or dimensionality improves performance as it allows more information to be stored. However, this comes at the cost of higher computational resources and memory usage. So, therefore, there is always a trade off between accuracy and efficiency, and also choosing the right vector size depends upon the application. That's it. So, the advantages of this is Glove has several important advantages that make it widely used. First thing is that it uses global co-occurrence statistics, which makes it more informative compared to models that only use local content. Second thing is it also captures semantic relationship between effectively such as analogies and similarities between words. Third thing is that it is computationally efficient and scalable, meaning it can be trained on very large data sets. So it also uses a weighting function which helps reduce the impact of very frequent or very rare words. So making that models more stable. So overall, Glow provides a well balanced and powerful representation of words. So, whereas limitations, despite its strengths, Glow also has some limitations. Firstly, it requires large data sets to perform well, which may not also be available. Secondly, it generates static embeddings, meaning each word has only one vector regardless of its context. For example, the word bank will be have some same representation whether it refers to a river bank or a financial institution. So this shows that Glove lacks context awareness, which limits its availability to handle ambiguity. Because of these limitations, more advanced models like BERT were developed, which generates context-based embedding. So the conclusion part is so to conclude, Glove is a foundational model in the fields of natural language processing. It successfully bridges the gap between global statistics methods and vector-based learning approaches. So it also captures meaning, similarity, and relationship between words effectively, making it highly useful for many NLP tasks. Even though newer models have been developed, Glow still plays an important role in building a strong understanding of word embeddings. And also, it remains a key concept for anyone studying NLP. Regardless of this, the glove has also the same similarities between the words to words relationship between every word effectively, which also makes many NLP tasks high.
Chimpanzee research paper in the field of deep learning and neural networks uh, and natural language processing. Titled Attention is All You Need, proposed by Oswani and colleagues in 2017. This paper introduced the transformer architecture and which completely changed how sequence data is processed. Before this work, most models relied on recurrent neural networks such as LSTMs and convolutional layers. So, however, this paper demonstrated that it is possible to eliminate both recurrence and convolution entirely and rely slowly on attention mechanism. So this was a groundbreaking idea because it enabled parallel computation, faster training, and better handling of long-range dependencies. So today, almost all modern architectures like BERT and GPT and large language models are based on transformer design. So in this presentation, we will carefully understand the motivation behind this model, its architecture, and why it has become the foundation of modern AI systems. So now we are coming to the outline. So in this presentation, we will systematically explore the transformer model. We will begin by understanding the motivation behind replacing traditional sequence models. So particularly focusing on this limitation of recurrent and convolution architectures. After that, we will study the concept of sequence to sequence learning and how it handles before transformers. So then we will move into the core of the paper, which is the transformer architecture itself, including the encoder-decoder structure and attention mechanism and positional encoding. We will also discuss key components such as multi-head attention and feed-forward networks. Following that, we will examine training strategies and the results achieved by this model in machine translation. So finally, we will analyze the impact of work and understand why it has become the backbone of modern machine learning system. Now coming to the introduction and motivation of this paper. So to understand the importance of the transformer, we must look at the limitations of previous models. Earlier, sequence modeling tasks such as mission translation were handled using recurrent neural networks. So particularly LSTMs and GRUs, these models process sequence token by token, meaning each step depends on the previous hidden state. So while this helps capture sequential information, it introduces several challenges. First one, this sequential nature makes it difficult to parallelize um, computations, which slows down training significantly. Second one is that learning long-range dependencies becomes difficult because information has to pass through many steps. So leading to issues like vanishing gradients, even through attention mechanism, were introduced to improve performance, and they were always used alongside recurrence. So the key idea of this paper was to question whether recurrence is necessary at all, or the authors proposed that attention alone is sufficient the model dependencies in sequence. So this led to the development of the transformer, which relies entirely on attention mechanism to capture relationships between tokens, regardless their position in the sequence. Now coming to the background sequence to sequence models, which is in traditional sequence to sequence models, the architecture consists of two main components, an encoder and a decoder. The encoder processes the input sequence and compresses it into a fixed length representation, while the decoder generates the output sequence based on this representation. In RNN-based models, the encoder reads tokens one by one, updating its hidden state at each step. However, this approach has several drawbacks. It cannot process tokens in parallel, so which makes training slow. So additionally, the fixed length representations can become a bottleneck, and especially for long sequences, as it may not capture all necessary information. So convolutional models attempted to address some of these issues by embedding parallel computation, but they still require multiple layers to capture long distance dependencies. So self-attention, on the other hand, allows each token to directly attend to all other tokens in the sequence. This provides a more efficient and flexible way to model relationships, so making it a powerful alternative to traditional approaches. Coming to the transformer architecture, the transformer architecture is built around the idea of attention mechanism basically. So it follows an encoder decoder architecture structure I already discussed in previous slides. So similar to previous sequence to sequence models, but replaces recurrence and convolution with attention layers. The encoder takes an input sequence and converts it into a set of continuous representations. So the decoder then generates the output sequence one token at a time, using both its own previous outputs and the encoder's representation. So each layer in the transformer consists of two main components. What are they means? A self-attention mechanism and a feed forward layer. So these layers are staggered multiple times to form the full model. One of the key advantages of this architecture is that it allows parallel processing of all tokens in a sequence, so which significantly speeds up training. Additionally, because attention connects all positions directly, so the model can capture long-range dependencies more effectively than RNN, and CNNs. So this combination of efficiency and performance is what makes the transformer so powerful.
Now let's see about encoder stack. The encoder is the transformer is composed of a stack of identical layers, typically 6 in the best model. Each layer contains two main subcomponents, a multi-head self-attention mechanism and a position-wise feed forward network. The purpose of self-attention is to allow each token in the input sequence to consider all other tokens simultaneously, thereby capturing global context. This is fundamental difference from recurrent models, where context is built step by step. Additionally, residual connections are added around each sublayer, which helps in maintaining gradient flow during backpropagation and enables the training of deeper architecture layers. And layer normalization is applied after each residual connection to stabilize training and ensure consistent feature scaling across layers. Let's discuss about decoder stack. The decoder is the transformer is also composed of multiple identical layers, but it contains an additional attention mechanism compared to the encoder. Each layer consists of three subcomponents: masked multi-head self-attention, encoder-decoder attention, and a feed-forward neural network. And the masked self-attention ensures that the model does not attend to future tokens, thereby preserving the autoregressive property required for sequence generation. The encoder-decoder attention allows the decoder to focus on relevant parts of the input sequence while generating each output token. This interaction between encoder and decoder is crucial for tasks like translation. Similarly, to the encoder, residual connections and layer normalizations are applied to improve training stability. Now let's see how the scale dot product works. And scale dot product attention is the core operation of the transformer. It operates on three inputs: queries, keys, and values. The idea is to measure how much attention a query should pay to each key and then use these attention weights to compute a weighted sum of values. The dot product between queries and keys gives a measure of similarity, but when the dimensionality is large, these values can become very large, leading to unstable gradients. To address this problem, the dot product is scaled by the square root of the key dimension. This ensures that the softmax function operates in a stable range. The result is a set of attention weights that indicate the importance of each token relative to others. Now let's see what multi-head attention is. Multi-head attention extends the idea of single attention by allowing the model to attend to information from different representation subspaces simultaneously. Instead of computing a single attention function, the model projects queries, keys, and values into multiple similar subspaces and performs attention independently in each of them. These outputs are then concatenated and projected back to the original dimension. This approach enables the model to capture different types of relationship in parallel, such as syntactic dependency and semantic similarities. For example, one head may focus on grammatical structure while another focuses on meaning. This diversity of attention improves the expressiveness of the model and allows it to learn more complex patterns in the data.
Coming to the positional encoding, one of the unique challenges in the transformer architecture is that it does not inherently capture the order of tokens since it does not use recurrence or convolution. To address this, positional encoding is added to the input embeddings. These encodings provide information about the position of each token in the sequence. The paper uses sinusoidal functions to generate these encodings, allowing the model to learn relative positions effectively. Each dimension of the encoding corresponds to a different frequency, which enables the model to distinguish between positions even in long sequences. By adding positional encoding to embeddings, the model gains the ability to understand sequence order while still benefiting from parallel computation. While the attention mechanism is responsible for capturing how words relate to each other, the feed forward network FFN acts as the processing unit that transforms the features of each individual token. In every transformer layer, this network is applied to each position independently and identically. It consists of two linear transformations with a ReLU activation in between. A key technical detail here is the dimensionality, that is, the network typically projects the data into a much higher dimensional space, often 4 times larger than the model's base dimension, before projecting it back down. This expansion and contraction gives the model the necessary capacity to learn complex patterns and nonlinear relationships within the data. Because the weights of the FFN are shared across all positions but the inputs vary, it effectively functions as a specialized processor that refines the context-rich information provided by the attention heads. The separation of concerns, attention for context and FFN for feature processing, is a cornerstone for the transformer's efficiency. Self-attention was introduced to solve the fundamental bottlenecks of traditional sequence modeling. In older architectures like RNNs, the information has to travel through a long chain of hidden states to connect the beginning of a sentence to the end. This leads to the vanishing gradient problem where the model forgets earlier words. Self-attention solves this by providing a constant path length. Every token in a sequence is directly connected to every other token in a single step. This makes it efficiently easier for the model to learn long-range dependencies such as connecting a pronoun at the end of a paragraph to a noun at the very start. Beyond connectivity, self-attention is highly optimized for modern hardware because it doesn't rely on the previous state to calculate the current one. The entire sequence can be processed simultaneously, leading to massive speedups during the training. Finally, self-attention offers a level of interpretability that was previously rare in deep learning. By visualizing the attention weights, the researchers can exactly see which words the model is focusing on to make a prediction, effectively revealing the model's internal thought process as it parses syntax and grammar. Training a transformer requires a very specific recipe to ensure the model converges and generalizes well to new data. The authors utilize the Adam optimizer but with a unique learning rate schedule that includes a warm-up phase. During the first few thousand steps, the learning rate increases linearly, and after this warm-up, it decreases according to the inverse square root of the step number. This prevents the model from making massive erratic updates early in the training when the weights are still random, which would otherwise lead to a crashed or unstable model. To further improve robustness, the transformer uses two primary regulation techniques, residual dropout and label smoothing. Dropout is applied to the output of each sublayer before it is added to the input, preventing any single neuron from becoming a bottleneck. Label smoothing is a more subtle technique where the model is discouraged from being too confident in its predictions. Instead of trying to predict a 100% match for the correct word, it is trained to reserve a tiny amount of probability for other possible words too. This prevents overfitting and helps the model perform better on diverse real world data sets that it hasn't seen during training.
So from the result slide, we can see that when we look at the hard data, the transformer didn't meet just expectations. It redefined them. On the WMT 2014 English to German and English to French benchmarks, it established new states of the art benchmarks. But the real now factors isn't just the accuracy, it's the efficiency. By moving away from sequential processing, we achieved these three results at the fraction of the computational cost compared to previous assembled models. So, this proved that attention based architectures are both more effective and significantly faster to train. So, from this slide, it mainly focuses on breaking the model down to see what make it ticks. So now we might ask which part of the transformer actually does the heavy lifting. Our evaluation studies provides the answer. We found the multi-head attention is the absolutely non-negotiable as we reduced the number of heads and performance dropped significantly. We also observed that models scales matters. More parameters generally lead to better results. Lastly, we confirm that dropout remains essential. Without it, the model is so powerful that is tends to overfit. So losing its ability to handle new unseen data. So the main key highlight of this slide is we need to explain that what is an ablation study is like taking parts out of a car engine to see which one is the vital for the speed. So from this generalization slide, you can see that proving it's not just a translation tool. So it is one of the biggest tests for any AI model is whether it can perform outside its primary comfort zone. To test this, we applied the transformer to English constituency parsing, a task very different from machine translation. Even without task specific turning or specialized modification, the transformer delivered highly competitive results. So this is a crucial finding because it demonstrates that the underlying architecture is a universal learner capable of understanding complex linguistic structures across various domains. So it mainly focuses on the word versa- versatility. The model understands language, not just translation rules. So from the attention visualization, it mainly focuses black box of a transparent. The one of the most beautiful aspects of the architecture is it's through attention visualizations. We can see that what the model is thinking. Different attention heads learn to focus on different things. Some track long ranges dependency across a sentence, while others focus on immediate syntactic relationship like matching a verb to its subject. So this visual evidence confirms that the model isn't just guessing; it actively learning the structural nuances of human language. So it mainly focuses on point to point line or head maps in the visualization to show how word connects to each other. So now we will conclude this. It mainly focuses impact and the future. To wrap things up, the transformer represents a fundamental shift in how we approach sequence modeling. By replacing the slow reoccurrence of traditional RNNs with the fast parallelization of self attention, we have unlocked the better performance and massive scalability. While we started with text, we are already seeing this impact ripples across the entire industry. From computer vision to speech processing, the transformer isn't just a model for today, it's the foundation for the next generation of AI. So from this slide we can mainly highlight that it is end with a strong confident summary of performance and training speed and scalability.
Overturn, which is a robust, optimized but pre-training approach This work was proposed by researchers from Facebook AI and the University of Washington. So the key idea of this paper is very interesting. Instead of designing a completely new architecture, the authors focused on improving an existing model. So, but is an existing model by optimizing how it is trained. So this is important because it shows that performance improvements are not always dependent on architectural changes, but can also come from better training strategies. So ROBUTA stands for a robustly optimized BERT approach, and it is demonstrates that with proper tuning, BERT can achieve or even surpass the performance of more complex models. Hello everyone, now coming to the outline. In this presentation, just we will first understand the motivation behind improving BERT and why existing comparisons between language models were not reliable. So then we will revisit how BERT works and including its training objectives such as masked language modeling and next sentence prediction. So after that, we will go into the core contribution of Roberta, which is including dynamic masking and removal of NSP, training with larger datasets and larger batch sizes. So finally, we will analyze experimental results on benchmarks such as glue, squad, and race, and conclude with the key insights. So coming to the introduction and motivation of this paper, the motivation behind Robota comes from an important observation. All through many models were proposed after birth, such as Excelnet and others, it was difficult to compare them fairly. So this is because different models use different datasets, different training durations, and different hyperparameters. So the authors found that BET itself was not fully optimized. In other words, BET was undertrained. So this means that its potential performance was not fully realized. So instead of designing a new model, the author asked a simple question: what if we train BERT prompts properly or using better data, long training, and improved strategies? So this led to the development of Robota, and which focuses on maximizing the performance of the same architecture through better training practices. Now we are coming to the background of BERT pre-training, which is a previous model of Robota. So to understand Robota, we first need to understand how BERT works. So BERT is based on the transformer architecture and is trained using a large amount of unbiased text data. So it uses a bidirectional approach, meaning it considers both left and right context when understanding a word. The input to BERT consists of two segments of text combined together and separated by special tokens like CLS and SCP. So BERT is pre-trained on datasets such as Bull corpus with and Wikipedia's and the fine-tuned on downstream tasks. So the architecture includes multiple transformer layers in BERT or in Robota. So attention adds and uses optimization techniques, then like Adam with learning rate, warm up and decay. Now coming to the training objectives of MLM and NSP. So BERT is trained using of two main objectives, that is MLM and NSP. So the first is masked language modeling, which is an MLM. So where a portion of input tokens, typically 15%, are randomly selected and replaced. So the model is then trained to predict these masked tokens. So the second objective is next sentence prediction, which is a binary classification task. The model predicts whether two sentences follow each other in the original text. However, the Roberta paper questions the necessity of NSP. So the authors found that removing this objective does not harm performance and can even improve it. So this insight is one of the key contribution of Roberta.
In order to improve BERT, the authors re-implemented it using a framework which is based on PyTorch. They carefully tuned hyperparameters such as learning rate, batch size, and optimizer settings. One important observation was that training was highly sensitive to certain parameters like Adam, appellation, and then also trained the model using full length sequences from the beginning rather than gradually increasing sequence length. Additionally, they use much larger datasets, around 100 GB of text compared to BERT's original 10 GB dataset. This large-scale setup allowed the model to learn richer representations. Static versus dynamic masking. One major improvement introduced in Robert is dynamical masking. In BERT, masking is static, meaning the same tokens are masked each time the data is used during training. In contrast, Robot A uses dynamic masking, where the masking pattern changes every time a sequence is fed into the model. This increases the diversity of training signals and allows the model to learn more robust representations. Dynamic masking also improves efficiency as the model does not need to duplicate data multiple times. Input format and NSP removal. Robert explores different input formats to understand the impact of NSP. The authors compared segment pairs, sentence pairs, and full sentences. They found that using full sentences without NSP performs as well as or better than other formats. This suggests that the NSP objective is not necessary and may even introduce noise. As a result, Robote removes NSP entirely and focuses only on masked language modeling. Now let's see the NSP analysis. The analysis of NSP provides several key insights. First, using individual sentences reduces performance because the model cannot learn long-range dependencies. Second, removing NSP does not hurt performance, which contradicts earlier assumptions. Third, using full sentences allows the model to capture richer context. These findings led to the decision to completely eliminate NSP from Robot A's training process.
One of the most significant departures Roberta takes from the original bird training recipe is the move toward batch sizes. While the original bird was trained with a batch size of 256 sequences, the Roberta authors experimented with sizes up to 8,000. Large batch training is physically demanding on hardware, but it offers a distinct mathematical advantage. It provides more stable and accurate gradient estimates during backpropagation. This stability allows for higher learning rate and faster convergence. To handle the immense memory requirements of 8K batches, the authors employed gradient accumulation, a technique where gradients are calculated over several smaller mini batches and summed up before the model's weights are actually updated. This effectively stimulates a gained batch without needing a supercomputer's worth of VRAM, leading to a much more efficient and scalable training process. Tokenization is the bridge between raw text and machine readable numbers, and Roberta optimizes this via byte level byte pair encoding (BPE). Traditional BPE used in models like BERT often relies on Unicode characters, which can result in a massive vocabulary or frequent unknown token errors while encountering rare symbols or emojis. Roberta instead treats text as a sequence of bytes. By using a vocabulary of 50,000 byte level units, the model can represent any piece of text without ever needing an unknown tag. This approach makes the model significantly more robust when dealing with diverse languages, technical jargon, or messy internet data. While this increases the embedding layer's parameter count slightly, the trade-off is a much higher level of generalization and the ability to process complex text formats that would break traditional tokenizers. Roberta stands for robustly optimized BERT approach, and its success comes from a combination of several iterative refinements rather than a single architectural change. The authors proved that the original BERT was actually significantly undertrained. Key improvements included the removal of the next sentence prediction task, which was found to actually hurt performance on downstream tasks, and the introduction of dynamic masking in the original BERT. The masking pattern was static and determined once during pre-processing. Roberta generates a new masking pattern every time a sequence is fed into the model. These changes, combined with longer training durations and more diverse data, demonstrate that the underlying transformer architecture is incredibly powerful provided the optimization strategy is tuned to its full potential. The secret sauce of Roberta lies in the sheer volume of data and the duration of its training. The author scaled the training data from BERT's 16 GB to a staggering 160 GB of uncompressed text, incorporating new sources like Common Crawl News and Open Web Text. More importantly, they discovered the BERT style models do not plateau as early as previously thought. Even after millions of training steps, Roberta continued to show improvements in both perplexity and end task accuracy without overfitting. This finding shifted the industry's perspective, highlighting that large scale isn't just buzzword, it is a requirement for deep learning models to reach their theoretical performance ceiling. It proved that proper training schedule and data diversity are just as critical as the model's code itself.
So from the slide glue results, moving on to the performance metrics, let's look at the glue benchmark. As many of you know, glue consists of 9 diverse natural language understanding tasks. Robot achieved state-of-art results here, but what's truly impressive is how did it. Unlike other models that rely on multiple tasks fine tuning to boost scores. Robot outperforms them using it coarse learned representations alone. So this proves that the model isn't just memorizing tasks. It has developed a fundamental deeper understanding of language syntax and semantics. So in this slide we have evaluated the model squad that standard question answering dataset. In this task, Robota reached the top of the leaderboard using a relatively simple setup. While previous leaders in the space often required massive additional datasets or highly complex architectural modifications to find answers in a text. So, Robota surprised them by a simple being better trained. This highlights the sheer effectiveness of the optimized training strategy we discussed earlier. It shows that a robust foundation is often better than a complex add-on feature. So in this slide, we have tested Robota's limit with the race dataset, which is particularly challenging because it involves reading comprehension questions from middle and high school exams. Unlike simpler tasks, race requires the model to digest long passages and reasons through them to select the correct answers. So, Robota's strong performance here is a correct indicator of its ability to capture deep contextual information over long sequences, proving it can handle the nuisance of and complexity of human level reading materials. So the end is conclusions and takeaway. So what is the big picture away from this research? The most significant finding is BERT was actually significant undertrained. By revisiting the original BERT architecture and applying better training strategies, especially more data, larger batches, and longer training times, we can say massive leap in performance. This tells us the optimization and data scales are just as critical to progress the AI in the actual design of the neural networks architecture itself.